going to be talking about some uniqueness questions of Croft, Falconer and Guy, and this is a joint work with Ryabogin, Stancu and V, Yaskin. And in the book Unsolved Problems in Geometry, Croft, Falconer and Guy talk about the following questions regarding a convex body. So we have K, it's in our N, but basically in the book they write in R3, but there's nothing, there's no problem in making this more generous. Okay, so convex body in Rn when n is greater than or equal to 3, and we have a collection of hyperplanes. A psi is a unit vector, and a psi is defined as the set of points in Rn such that x dot psi is equal to some value t. So we have hyperplane perpendicular to psi at distance t from the origin, and t may depend on the particular psi you're taking. And they say assume that K and the collection of hyperplanes satisfy some specific conditions, one or possibly more of the following conditions. So the first condition is a volume condition. It's the usual condition for the floating body problem. Is all hyperplanes cut off the same volume out of K from K. So here if we define the subspace H plus, which would be the same with a greater than or equal right there, what we have in this condition is that for every psi unit vector, the volume of K intersection H plus, and we're going to normalize it, divided by the volume of K is equal to some constant delta that is independent of psi. Alright, so that would be cutting a constant volume condition. Another condition we may have would be condition A. We have that the area of each section of K by this collection of hyperplanes is some constant, again, independent of psi, constant area condition. Or we could have what they call condition I, moment of inertia condition. All the sections have equal constant moments of inertia. We can have dimension condition P. All sections have equal perimeter. Well, they set up the problem in R3. But anyway, you can generalize. I'm not going to talk about this one a lot. Of sections, K intersections by the hyperplane have equal perimeter. You can come up with any such conditions that you would like about your convex body. We're going to introduce one that they didn't mention, but it's going to be useful for us. The distance from the hyperplane to the origin is some number t, which is positive and it's fixed, again independent of psi. So, for example, if you have conditions V and H, so you have your convex body, all hyperplanes have the same volume and are at the same distance from the origin, these two conditions are saying that the floating body of K is a ball of radius t. I'm going to introduce the floating body in a moment, but before we get to that, what Croft, Falconer and Guy ask is it true that if we assume any two such conditions, so you have your family of hyperplane, but your family satisfies two of them, not just one. And they ask, does it mean that K must be a Euclidean ball? And in all this talk, I'm going to denote Euclidean ball by B, and this is the unit Euclidean ball. Well, they also made the following observation.
it's maximal with respect to this condition. What are you assuming with the family? It's a maximal family, or it can be one hyperplane?
You are given a collection of hyperplanes, one hyperplane in each direction, and
oh, it's for each direction. Okay.
Yes,
Okay.
just for your collection. But you're assuming the same family satisfies two of these conditions, or as we'll see, possibly more. So they also make the observation that if you have conditions VI together, this is equivalent to Ulan's floating body problem. That says that asks whether a body, convex body that floats in equilibrium in all possible orientations, whether it must be a Euclidean ball. So then we can see that in general, having two such conditions doesn't necessarily imply that your body is Euclidean ball, because we have a counterexample to Ulan's floating body problem when the density is 1/2, so your hyperplanes are cutting half of the volume of K. So there's a counterexample by Dima. So in general, you cannot expect the answer to be yes to the original problem as they posted. The same technique used for the counterexample to Ulan's problem can be shown to work for problem VA. So you can construct a body of revolution, which is a perturbation of the ball that satisfies these two properties, but it's not a Euclidean ball. So more perturbations, also no for delta equals 1/2. On the other hand, in the class of bodies of revolution, if you assume conditions PA or conditions AI, the answer in this class of bodies of revolution is yes for every density, because basically you have an isoperimetric inequality that you can use. Since your bodies of revolution, you know one of your sections is a disk, and among all sets that have equal moments of inertia, this maximizes the area. The same thing happens with the perimeter. All these three results are by my student, Ryabogin. On the other hand, if you pose additional conditions, in the case of Ulan's question, it has been known for quite a time that the answer is yes, if the body is origin symmetric. This was Snyder and independently Falconer. There are also results, different proofs given by Stancu. I'm sorry if I misspelled it. Ryabogin, and also by Florentin, Werner, and Jack. This is for general dimension N. So it seems natural that if in general two conditions that give an affirmative answer, you can add additional conditions such as this one in order to get the affirmative answer, or being in the class of bodies of revolution, although that doesn't work for these counterexamples because those are bodies of revolution also.
To which hypothesis does the yes with the additional symmetry refer?
This one.
Yeah, but to which of the other?
So I'm still talking about problem VI.
VI.
Problem. All right. So one of the things I want to present in this talk is a result if we have three conditions that are this. I'll present the proof of VIH. The other is very similar, and there's limited time. Only this one we prove an affirmative answer in the class of bodies of revolution, and only for dimension 4 at this point. Okay, but before I get into the proof of this, I want to talk about another possible approach. All right, let's see if I can. I won't be able to take it down later. All right. So, no, this is good. That's good, I think. So erase the first announcement. So the other approach follows a result by Kurusa and others. They prove the following. They assume additional normalization conditions on the body. So you have K, you have a convex floating body such that the volume of K is equal to the volume of the, let's say, unit Euclidean ball. We can rescale things. Then the floating body of K at the level delta is the same as the floating body of that ball for the same delta. And then the surface of centers, I'm going to introduce the notation in a moment, of the K is also the surface of centers of the ball, and they prove that K is the Euclidean ball. So for the purpose of this talk, since in all our questions the floating body is going to be a ball, I'm going to use Dupin's original definition of floating body. So when you have your collection of hyperplanes, it's a collection of hyperplanes chopping up a same proportion of the area delta, well, it's supposed to be the same. The floating body, do we have colors? So you would have that the floating body is the envelope of your collection of hyperplanes, and that's going to be sufficient for our purposes. So this is K delta. And then what is the surface of centers? For each piece that you chop off, so if you imagine this is the water that your body K is floating in, the volume has density delta, there's a center of mass C delta on the underwater part, and you can do that in all directions, and the body whose boundary is the locus of all these centers of mass that are underwater, this would be the surface of centers at the level delta of K. All right, so our first result is that we can prove the same thing, but we don't need these hypotheses. And I'm going to go over the proof. So the assumptions are exactly the same, so I'm not going to copy them again. I'll just start with the proof. So we don't need assumption on K delta. So how does the proof go? So because of our normalization condition, if we have the volume of K times delta, this is equal to the volume of the part that we're chopping off from the body, and this is true for all sides. All right? So, but we have exactly the same thing for the unit ball. Those volumes are equal, and this is just this. Okay, so all these quantities are equal. We're going to average them over the sphere, so we still get the same quantity. I'm going to consider that on the sphere we put the probability measure. So we have integral over Sn minus 1 of volume K intersection. This is again the same thing we started with. All right. Let's side. And now, okay, so let's write this integral as the integral Sn minus 1 big psi. And here, what do we have? This is the set. Is it still upstairs? Yes. Of all the points, such that x dot psi is greater than or equal t. But now, because we have the assumption on the floating bodies being equal, we know that t is constant. It does not depend on psi for this proof. All right? And this is the x. So just for convenience, we're going to normalize x, make it a unit vector. Still nothing changed here. And let's change the order of integration. We're going to change the order of integration, and we're also going to make a change of variables in this form. All right? So what we get? We have an integral over k minus the floating body, which has radius t, because that was the condition we had here. We had a t, distance to the origin. And then here we have an integral on dy, where y starts at t over x, so this is the x, t over magnitude of x, ends at 1, because both are unit vectors, and then we have this factor that shows up, and minus 3 over 2. All right. So the next step is to pass the polar coordinates in the outer integral. So we have integral over s minus 1 d theta. Here we have integral from t to the radial function of k, so that's where we are integrating. R to the n minus 1 dr, and the inner integral stays the way it was, like this. Now, the observation that comes next is that if you define this function that's defined as the two inner integrals, r to the n minus 1 dr, t over r1, this thing is the same term, and this function is defined for x greater than t to the power n. So because those are our limits of integration there, this function is convex, and you can just check it directly by taking two derivatives, and it's kind of straightforward. So we have that this is a convex function in the domain we're at. So what we have here is here the integral over Sn minus 1 f of rho k psi to the power n, so theta, d theta. Agree? But now, since this is convex, we apply Jensen's inequality, and we take the f outside. Okay, but now remember that from the beginning, we started assuming that we have the same equality for the ball. So I have just rewritten all these integrals. Here you have the same thing for this one, which is 1, and for this one, which is again 1. So we're getting equality in Jensen's inequality, and from there it will follow that rho k has to be constant. And that's the end of the proof. Okay, so that's one of the results. Yes?
This surface of centers, this was by introduced by Han Huang, right? And Dan Florentin, as far as I remember, or
it wasn't Slonka and
oh, sorry,
Slonka,
yeah,
yes.
it was Slonka and Han
Slonka and
Huang.
you.
Yeah, right?
Yes.
Yeah. And so you use the Dupont's definition of floating body here.
Yes, but
and you
basically
and
because
you don't have any problem because you assume.
I'm assuming that the
equal to
floating body is the
ball.
ball, so I don't need to. I mean, just for the purpose of the talk and say it quickly. Yes. So let's go back to the probability conditions now. So let's clean this up. Okay, so next theorem, theorem 2. We said we have K is a convex body in R4 of revolution with C1 boundary. And we are going to assume that the floating body of K is a ball, so with radius r. The surface of centers of K is another ball, R1b. Let's say if R delta is less than 1/2, then R1 is greater than R, so delta is between 0 and 1/2. This is, we have a whole range of deltas, so it's not just for 1/2. Both balls are concentric. Balls are centered at the center of mass of K. Okay? And then we prove that K is a Euclidean ball of some radius. Now, what is different from the previous result that was following Kuruja and other? They had to have a very specific normalization condition on the volumes and the radius of the floating body and the surface of center. Here, there's no condition here on the radius. We just say it's a ball. Okay? So, how does the proof go? We have first to introduce coordinates for a body of revolution that will be convenient. And so we have a body of revolution. The axis of revolution is the axis x1. We have a concave down function f that prescribes the boundary of our body. And we're assuming our floating body is some ball of radius little r. So what we have here is that our collection of hyperplanes are tangent to this floating body. Because this is a body of revolution, each hyperplane is determined by a line like this on this plane that we can write as xn1 plus h of s. And because the floating body is the ball, we know exactly what this ordinate is for them. This is r square root of 1 plus s squared, where s is the slope of the line, and s is between 0 and infinity. So we have to introduce a few more notations. We're going to call, when you fix your slope x, y of s is going to be the x1 coordinate of the point of intersection of your hyperplane with your body. And here the same thing. We have minus x of s is the x coordinate. So clearly, because the f and this line intersect each other at those points, we have that f of s is equal s y of s plus h of s, and minus f of minus x of s is equal to minus s plus h of s. And our h being prescribed, if we determine what x and y are, f is completely determined by these two equations. Another thing I'm going to mention is, so on the picture, you get a different color again. So if we have, this is the origin, we're putting the origin at the center of mass of everything. If this height is the ordinate h of s here, then the x-coordinate of a point of tangency of this line with the floating body is minus h prime of s. We'll be using this information. So, we want to to come up with a system of two integral equations that correspond to our assumptions that, like we said, are VIH. It's equivalent of what we have there. The condition that the volume is constant, this was proven by Dupin to be equivalent to the fact that the envelope of all these water surfaces is exactly the centers of mass of the sections. So what we have is that the center of mass of K intersection H of, I'm going to put it in terms of LS, because we have this specific equation, you can just take two nearby planes, take their limit, and find out where the center of mass of the intersection of them is, what the limit approaches, and you get that it's minus h prime of s, 0, 0, ls of minus h prime of s. So we have the centers of mass. This is the condition that the volume is constant. And we can write this easily as an integral equation. So the first coordinate of the center of mass, which is the only one that we need, would be the volume of the section. This is minus 1 integral of x1 over this section. All right, so we can here move this volume to this side, and minus 1k intersection h side, and write it as an integral. Can I erase it something like this? Write it as an integral, and then if you take vertical slices with the hyperplane x1 equals t, the intersection of this hyperplane and this hyperplane that's based on ls is an n-2 disk that has radius square root of f squared minus l squared. So using this observation, we can write this integral as, let me put it here, the integral from minus x of s to y of s, t, that's how we're cutting, f squared of t minus l squared of t to the power n minus 2 over 2 dt, and writing the same thing, this as an integral, and passing this to the right-hand side, here we get h prime of s plus t, and we get a 0. And this is our integral condition, expression of the constant volume condition. All right, and because of the sake of time, you can get similar equations for the moments of inertia, and I'm just going to write what it is. Actually, I'm going to write the first one. The first moment of inertia is some constant 1 plus s squared to the 3/2, an integral from minus x to y. And here what we're integrating is t plus h prime of s squared, and then s squared minus l squared, same power. This is equal to constant, because we're assuming constant moments of inertia. And whereas we have condition I, all constant moments of inertia are the same, so this is the only equation we need. So now we have this system with two equations, and if we differentiate each of the equations twice with, yes?
This formula is true in dimension 4 or in...
This formula is true in any dimension, but you see why we like 4. Right? So in dimension 4, all these exponents are just 1. And when you take two derivatives with respect to s, the fact that f and l coincide at these endpoints means that f disappears completely after taking the derivatives. So we end up with a system of ODEs like this that involves the derivatives of the functions x and y with respect to s. And I'm just going to wave my hands from this point on. dy prime equals q. So what do we have? P and q are polynomials on x and y, can be computed completely explicitly, and they're rational functions on the square root of 1 plus s squared, which is the term that appears all the time. So these are polynomial, these are rational functions, there are no derivatives involved here. And then the terms A, B, C, and D are such that what you get here is some product involving X. Let me see how this goes. Minus H prime of S, Y plus H prime of S, Sx plus H of S, minus Sy plus H of S, which, like you see, the last two terms are the vertical coordinates here. Those are not zero if S is between 0 and infinity. And similar, the other terms are these distances, which again are non-zero if S is between 0 and infinity. So this determinant is never 0. So we have a nice system. If you provide some initial values for some slope S0 in this interval, 0 plus infinity, and then you have two different, another different initial values at the same point, you're going to get two different solutions. But our problem here is these solutions could potentially converge to the same thing as S goes to infinity if the system is asymptotically stable. So, but the issue why is that an issue for us? Because our Cauchy condition for our system is given at infinity. We know exactly what happens when your section is the disk for the body of revolution. What happens at infinity is that, let me write it like this, x of infinity equals y of infinity equals the radius of the floating body. So it would be bad for us to have two different solutions starting on a non-infinite slope that join together at infinity, because then we cannot prove anything. So the rest of the proof that I'm not going to get into details is just very technical, doing two more changes of variables in this system and starting to find inequalities, boundedness inequalities for x and y, or whatever they get transformed in the new coordinates, that show that if you assume that there is a solution which is not the one corresponding to the ball, you end up getting a contradiction because you get that x and y are unbounded, which they cannot be if you look at this geometrically. So like I said, that's too technical, so I will stop here.